session. My name is Ram Seshadri. I'm a professor in the University of California, Santa Barbara, and it's my pleasure to be chairing this session. It's a particularly special pleasure for me because the first speaker is someone I've known for a long time, Professor Claudia Felser, who's from the Max Planck Institute in Dresden for the chemical physics of the solid state. And Professor Claudia Felser is one of the most well-known people in the area of topological materials, but also magnetism writ large in materials. And she's highly recognized. Only recently, she's been elected both to the US National Academy of Engineering and the National Academy of Sciences as a foreign member. She's also a member of the German Society, the Leopoldina, and she was recently awarded the Max Born Medal, which is a joint medal of the Institute of Physics in the UK and the German Physical Society. So she's going to tell us about her research on topology and chirality.
Yeah, thank you very much, Ram, for the nice kind introduction. And I also want to thank the organizers for having the opportunity to come to this nice place. So I especially thank the Jake, so that he always organized this meeting. And I hope next year we can come again with the students, because for us it's already an event, but for the students it's even a bigger event. No, to see the Jake in person, to have dinner with him, I think this is a unique opportunity in life. So I'm happy to talk today about topology and chirality. So I'm a little bit far away from magnetism this time. Everybody knows we are in the field of topology, but we want to connect it now with chirality. And this is also good because I want to make a connection to the speakers before. So they spoke a lot about organic materials, and we know we can make these organic materials, which can be like the right and the left hand. They are like mirror images, and so this you need also, or we have also in biochemistry, in all the biological molecules in our body, and what we eat is chiral. But on top, we learned already from Ben very nicely that even the motors are chiral, and also on a higher level of organization in the body, everything is chiral. But there's still the big magic about this, so we cannot explain how chirality came into life. So, but my viewpoint is a little bit more on the solid. So crystals can be also chiral. They can also have no mirror planes, and I want to make this connection, and maybe in the future we can do even more between molecules and crystals. And I have already started before with this, and I have a slight collaboration with Ben List, and this is simply an example. So he got the Nobel Prize this year for chemistry because he did asymmetric catalysis, homogeneous asymmetric catalysis. We already heard about the distinction homogeneous catalysis and heterogeneous catalysis, and we did some experiments in the direction of topology and solids, and eventually also asymmetric catalysis. But there is more fundamental broken symmetry and chirality on Earth or in the universe. And one very important experiment in high energy physics was the parity violation. It was shown by Wu, Professor Wu. She showed that there's also an asymmetry in the beta decay of the cobalt nuclei. So it depends from also here we can have this asymmetry based on the weak force, and some people even in organic chemistry might think that it's eventually the origin of the asymmetry in life, because the weak force of two chiral molecules is different, but the energy difference is very, very tiny. So far it was difficult to detect. But also I want to make the bridge to Andre's talk. So we can make super chiral molecules by making twisted graphene if you have twisted graphene on boron nitride. So this might be also a possibility to learn much more about chirality beyond the very nice physical properties. So people have heard eventually about twisted graphene, that this shows superconductivity and a quantum anomalous Hall effect, something which we expect in magnetic compounds and not in a non-magnetic compound which has only carbon. And this is really unusual because carbon is a light element and it's also not magnetic. And this comes then to my point. So we are chemists who like physics a lot. So normally we get a Hamiltonian from the physicist. The physicists are interested in a certain Hamiltonian, and just recently we became very interested in finding solution of the Dirac equation, and then we try to make corresponding crystals to investigate the potential solutions in these crystals. And recently we are mainly interested in topology, where there is this famous Bike boundary correspondence. So we find very unusual surface states in these materials, but also another important property is that in the electrons, the spin and the momentum is locked. So we cannot investigate what people are looking for in high energy physics, but we, in some sense, don't look for the particles. We look for quasi-particles, excitation, so we don't look for the hen. We look for this hidden hen here more in the single crystals. And this time I have a focus on chirality, which is here symbolized by the snakes. Yes, no, not snakes. It's anyway, by the shells of the. But what we do is then we apply also external forces to the crystals, like temperature, magnetic field, electric field, light, or strain or pressure. And the concept of topology comes to be even more interdisciplinary from mathematics. It deals with surfaces of objects. So like you see here on the right side, that a German pancake, for example, is simply like a sphere. It has a very simple surface, and it has a similar surface that's compared to this object. But if you have a donut, the American version, so we have a hole, so we have a different surface, and this has the same topology that like a coffee cup. And then if you go to South Germany, you have the pretzels, or in America, you like also pretzels. So we have 3 holes, and there's a second corresponding object. So this is what is used now, transferred into the electronic structure and made a big new field in condensed matter physics. And we still think that there is a need to make the bridge to chemistry. And this, I hope I give you a little bit the taste or some inspiration for the chemist that this might be a future direction. So from all the materials on inorganic materials, there's already a characterization, whether they are topological or trivial, or whether they even somewhere in their band structure are topological. And recently we start also to look for magnetic materials. So because this is a little bit more complicated, because we have to include some correlation effects and so on. So more or less all the inorganic materials are characterized so far, but no organic materials and beyond, morphs, coughs, whatever. So from these materials we can say from all the materials in the database, 25% are topological, but if you take into account that we even could change the Fermi energy, you can make more or less everything topological. This is what the assumption of the physicist is, but we chemists also know that doping has this limitation in material science, so we cannot move the Fermi energy always like we want. So the concept of topology, as I said, we like the Dirac equation, so we like relativistic effects, we like spin-orbit coupling, therefore many of the materials have heavy elements, and a typical electronic structure then for this materials are that we have an overlap between the conduction band and the valence band. This is the valence band, the symbol, and this is conduction band, and then you have this overlapping area, which is a so-called nodal line, and depending on the symmetry of the materials, and this I honestly learned from Roald Hoffmann, a chemist, okay, so that forbidden crossings are everywhere, and materials can open up band gaps by structural distortion, or nowadays, so we have in topology the spin-orbital coupling, so therefore we need the Dirac equation and fully relativistic calculation. So if this whole area is a so-called forbidden crossing area, and this is related to the symmetry of the crystal structure and therefore the symmetry of the bands we have here, then we can have an insulator which has a part of the valence band in the conduction band and a part of the conduction band in the valence band. And this insulator, and I already mentioned this famous Bike boundary corresponding, this insulator has very unique surface states which are connecting the valence band and the conduction band, so it's not like normal surface states simply connecting valence band. So conduction band or are somewhere in the gap. They really connect valence band and conduction band. And this leads to this very topological protected surface states, which are also spin polarized, so, and where the spin and the momentum is locked. But if we have other symmetries like rotation symmetries, it might be that certain points in this nodal line area are still allowed to be degenerated, and then we can get the so-called Dirac semimetals or Weyl semimetals. And the Dirac semimetals is if these degeneration points are at high symmetry points, which means the materials are very often centrosymmetric, and in Weyl semimetals, these degenerated points are at low symmetry points. So we can transfer even a Dirac semimetal into a Weyl semimetal by applying strain, so by reducing the symmetry, making a centrosymmetric crystal non-centrosymmetric, or by applying a magnetic field or something else. So these Weyl points are very interesting because as we have here spin momentum locking, so we have here chiral points in the electronic structure, which are, for the experts, are like a source and a sink, like magnetic monopoles. And here the electrons have two different chiralities, because if the spin and the momentum is locked in an electron is chiral. And this is a nice thing. So we have heard about chiral molecules, but we are also interested in chiral electrons. So, and this leads to, if we here have our crystals, in the bulk electronic structure, we have these Weyl points, and this also has a bulk boundary correspondence. In this sense, we have here now Fermi arcs, because this system is topological between these 2 points in the electronic structure, and so the surface states are Fermi arcs, and they are connected through the different surfaces of the crystal. So it's now very interesting to have these Weyl points far from each other, because then it's not so easy to annihilate them. And this is especially the case, what we will learn today, in chiral crystals, but also in magnetic crystals. It's better than in non-magnetic crystals. So therefore, recently people are working on Weyl semimetals in magnetism and in chirality. So this was what I said. So the spin and the momentum is locked. So this is like a movie from Maya, but it was inspired by some wordings or slides of Shushen, who said if the electrons are the spin and momentum are locked, the electrons behave more like on a German Autobahn. Everybody stays in his lane, and the back scattering is not allowed. So in some of the systems, we therefore see very, very large mean-free passes, and even recently people found in topological chiral crystals micrometer long mean-free passes which were fully spin polarized. So one thing why Weyl semimetals are so interesting for me is because, again, it's fundamentally connected to chirality and parity violation. And this is here. So the solution of the Dirac equation is also a possibility to explain the asymmetry between particles and antiparticles in the universe. So if we have here the vacuum state, and I'm sure the physicists are better experts for this, so we can have this Dirac equation here for the vacuum dispersion, and people normally ignore this lower part in the Dirac equation because we only see particles in the universe, but people try to show this chiral anomaly nowadays in heavy ion collision in high energy physics. And the chiral anomaly is simply if you apply a so-called E dot B term here, so you see an anomalous non-conservation of a chiral current here. And so this is like you can make an asymmetry between particles and antiparticles. This we cannot do in solids, but what in solids and in Dirac and Weyl semimetals, people are interested to look for the quasi-particle excitation, and we look for electron and holes, and our velocity is the Fermi velocity and not the speed of light. But we try to investigate this proposal, which was originally proposed here for pion decay, and nowadays investigated, as I said, for a heavy ion collision, so in solids. And all this is based because our electrons, if the spin and the momentum is locked, are chiral. So therefore, if we have a Weyl semimetal, if we make a Weyl semimetal, we try to look for different features which are related to the chiral anomaly, which are then translated by Bokov and Leon Balance, for example, into measurements or features in a solid. So we look that we see, or the proposal was that we see giant responses to external stimuli. We see this Fermi arcs, which I already explained before, but we see also this chiral anomaly. This is like if you apply a magnetic field experimentally and an electric field in parallel in the solids, you observe an asymmetry between electron and holes in these Weyl semimetals. And if you, there's even a further proposal, which was based on some work of Zubair Sachdev, that you see this axial-gravitational anomaly if you apply on top a temperature gradient, again leading to an asymmetry between the electrons and holes in the Weyl semimetals. So this was done by several people, but we also looked for this, and I simply use this as an introduction. So this is a non-magnetic Weyl semimetal. It's a big family, niobium phosphide. It was very easy, simple to make by chemical vapor transport. And the first thing which we saw in our samples was this giant response. If you see here the resistivity versus the temperature, and this is a 0 Tesla measurement, you see it behaves like a metal. It looks like metal. You see some wiggles here, but these are not wiggles. These are nice quantum oscillations. So we exactly know the band structure of these materials because we can transfer these wiggles into the band structure. But if we apply a magnetic field, we can strongly increase the resistance in this material. And then if we have, for example, 9 Tesla, we have a kind of plateau, which we know from the topological insulator, so which means so it's insulating in the bulk and probably has some metallic surface state. But we like this compound especially because it shows still a big response at room temperature, and as chemists we always look for something which shows big responses at room temperature, because this big responses, for example, in magnetic Weyls we can use for Nernst effect, and we see already giant effects in the Nernst effect, and this is all based on the topological properties, so we go far beyond what was expected by conventional theory in these materials. And then the next step is to look whether we have Weyl points, and this we do by Engel-Resolve photoemission. This is looking for the linear dispersion of the bands here, like in niobium phosphide, tantalum phosphide, and tantalum arsenic. And we see even a band splitting, which is related to spin-orbit coupling. And you see here also, if we make the elements of the materials heavier, we see a stronger splitting. And here is a calculated Fermi arcs, but the Fermi arcs are here quite tiny, so the distance is small in this material. And here we see then the Engel-Resolve photoemission data for this connecting the Weyl points in the bulk on the surface via this Fermi arcs. So then we looked for the chiral anomaly. So we did made a wire of niobium phosphide, and we did this parallel E.B term. So we applied the magnetic field in parallel to the voltage, and we saw the predicted B square behavior in this material. And the same is like, I don't want to go into details, this is simply if you want to ask question later. And then additionally with the temperature gradient, we saw exactly also the prediction that you see this B square behavior as a function of a magnetic field, and then it turns over and goes where it's a 0. So for example, in bismuth itself, you can make bismuth a Weyl semimetal by doping with antimony, and the group of George Hermans even shows this effect up to room temperature. For example, this thermal version of the chiral anomaly. So this was for us already interesting that you can see these features in materials, and we thought, can we use this in the future maybe for something that we have this chiral electrons and maybe connect it, and this is our plan to maybe chemistry and catalysis. So we did some catalysis already on this, but I have not the time to talk about this since I want to focus on the chiral system. So this even brought us into the New York Times because our co-worker were IBM, and they have very, very good advertising and PR department. We would never have made it, and so on. But you also can do the chiral anomaly optically. So we are now having also chiral light in our lab, but this is very nice work of New Gedek. So they simply applied circular polarized, right-handed circular polarized light and left-handed circular polarized light. They made the same kind of device, and depending from the polarization of the light, you have the current going in this direction or the current going in that direction. This, I think, is a very beautiful experiment. We did this on tungsten telluride too, also with Aaron Kapitolnik, and as I said, we want to do now even more, because as a chemist, I like circular polarized light to talk to the electrons, and at the same have the opportunity maybe to get an interaction to molecules very much. So another area where we work together, again with Andrew Bernowik, who is the theoretic mind behind this, and Maya, and so on, and Bob, and me as a chemist, so that we looked, can we have more beyond the Weyl points and the Dirac point? The Dirac point is a fourfold degenerated point. Chiral Weyl points has two degeneration in the band structure, and people who deals with spaghettis even got trained by Roald Hoffmann. They know there are many spaghettis where you have even sixfold and eightfold degeneration, and this has led to this publication beyond Weyl fermions and Dirac fermions, so that we might see new interesting properties in these new fermions. And even if you have a chiral crystal, so you have no mirror plane, so you can have these Weyl points at different energies. So this was a theoretical prediction, which has also got a lot of attention, but at this time we were aware that there are very nice chiral crystals, because I was also working on skyrmions with Stuart, and there's this famous chiral crystal structure, the B20 structure, where you see this very nice topological features in magnetism in real space. So far, I mainly spoke about band structures and reciprocal space, but there's also non-centrosymmetric superconductors, and we have this B20 structure, which looks here nice. We have made a figure which shows you that it looks like a kind of helix, say, even connecting atoms, which you might not have to connect here. Anyway, so this gave us also a very nice commentary from Carlo Benacker, who said, look, if you go beyond Dirac and Weyl, so this solution is not existing in the universe, because the universe has no crystal, it has no lattice. So he brought up the citation of Werner Heisenberg, who said, if we could apply a lattice on the universe, we might have even new fermions, which can help to morph protons into photons and whatever, but I don't think that we ever do this. But I like the citation very much, because I didn't even know before that I could look for new fermions beyond what was existing in high energy physics and astrophysics. Anyway, so here, if we do this chirality, combining chirality and topology, so people who are interested in chiral crystals, they are always interested because in this nonlinear optic properties, so we can here maybe combine this unusual surface state, and I already talked about this photogalvanic effect, which is extremely large, and also depending on the chirality of the light, so we can have even totally new effects. And the major difference between Weyl semimetals and this chiral topological semimetals is also that the points, the Weyl points, the chiral points are at different energies, so they spread over much larger energy range, and therefore we can expect new properties, even like a quantized circular photogalvanic effect. Okay, so luckily we were able to grow from one crystal even two chiralities. This is palladium-gallium, where we could have the right and the left-handed. So I have to honestly say it's more or less still statistics. So I think with Kochalski, we didn't have Kochalski yet. You can use a seed crystal to get especially one chirality, but it's still a debate even in our institute whether it's possible or not. The interesting thing is both chiral crystals have the same band structure, and this is the whole trouble why we cannot separate one enantiomer of a molecule from the other enantiomer, because the electronic structure is totally the same. So if you draw your molecular orbital diagram for one molecule, it's just the same as the other one. So the band structure is exactly the same. But if we have topology, there's a small difference, because therefore, if we look here for the chirality of the Weyl points, and here we have the two Weyl points at different energy, so the chirality of the two Weyl points is different. So we can distinguish the two crystals by their, I have to prove it. But first of all, it's the case. So you see this is a light blue chirality, and this is a dark blue, and here it's vice versa. So anyway, so this has led then also to some conclusion, as you saw the figure before. So this means like if I have the one crystal, so this dot is light blue and this is dark blue, so the chirality of my electrons are different, which means also if you draw the electronic structure, so here the Y points are not at the same energy, even at different points in the reciprocal space. This is again the reciprocal space, my Bryan zone, and it's inverted. But this leads to another interesting property, not only what we call the Berry phase has different signs, it has also that the surface states are chiral. This was for me surprising, and I didn't find anything about that you can have chiral surface states before, but it's even in trivial materials that the surface states are chiral. I checked it for the non-topological, the insulator, iron silicon, it's the same. And indeed, this is what we see. If we do angle resolved photoemission, and this is a band structure, we cannot see the color of the Y points, we only see the Y points. But if we look for the surface state, we see that the surface states are chiral for the different enantiomers. So we have different chirality of the surface state for the two enantiomers. So this was done on palladium gallium, but we had another collaboration with crystals on rhodium silicide and cobalt silicide. So they are also having these points here at different energy, and with Hassan's group, and they also could nicely show that we have this Fermi arcs, which are depending, they are chiral. And the other thing is also this Fermi arcs go all over the Bryan zone, so the Y points are really so far from each other that they spread over the whole reciprocal space. So therefore, there is no way to annihilate them. They are at different temperature, and they are all over the Bryan zone. And the band structure looks quite different, you know, but they are still related via topology in this chiral crystal. The other thing, this is maybe more for the experts who are in topology. This was also very interesting because we have this, with this higher fold degeneration. On one point, it's a 6-fold fermion. On the other point, it's a 4-fold fermion. And they had a Chern number which was higher. So like it was not only a donut which we discovered the super bretzel. So in this sense, we had this higher Chern number. So it was interesting to prove that we have this higher Chern number in this material. And they have different signs at these different points. We prove this in photoemission, and indeed we can prove it for the surface state. So we look very careful for the surface state. So one surface state has a negative slope. I don't show here the other one, has a positive slope from the other Chern number, which gives you already the sign. And since we see the splitting here, we even could show that our Chern number is +4 and -4 in this material. You see the same also in STM, and this is interesting if you go to a defect, and this makes a connection now why I'm quite excited about catalysis. If you go to the defect, and this is nice work in collaboration with Stuart's group, so then you see already in the scattering vectors and so on, you see already if you have both different chiralities of the crystal, you see that the defects are in some sense chiral. I thought maybe there should be a chance at the end of the day to do something with these materials. Okay, so the other thing is the Berry curvature is also different, which is magic for the physicist, but not so interesting for the chemist. But the Berry curvature, this magic property seems to be related with the orbital angular momentum, and therefore we calculated the orbital angular momentum here again, also down there for both chiralities, and you see they also behave like the mirror pictures. So also there we see a difference. This is distinguished, I think, for molecules. We see a difference in the two chirality of the crystals. And we see it also if we do with circular polarized light photoemission, we also see that we have a mirror picture of these both crystals. So this, I think, was quite interesting for us. If we think about, nobody did heterogeneous asymmetric catalysis yet, but I think there are SOE reaction, honestly, but not really systematic. Maybe this is interesting to see. At the same time, this is also for the physicists, we saw this predicted quantized circular photogalvanic effect in semimetals. It's not perfectly quantized, it drops even there. This is because we still have problems in the solids that we have not only our topological bands there, we also have other bands crossing, which very often gives some disturbance here. So, but anyway, this is maybe also more materials design and so on to get it better. Okay, so we thought already with the white semimetals we are interested to do catalysis, and we did catalysis on the white semimetals and even in the magnetic field, because if you see a magnetoresistance effect, you should be able to influence the catalytic properties in the magnetic field, and we did, and we saw it. Anyway, here I show the results for the chiral surfaces, and the reason also why we thought catalysis might be related to some spin orbit coupling and eventually to topologies, because we already, as I said, there are many materials already which are topological, and we did in 2015 investigated gold and platinum, and if you see here they are topological in gold and platinum. We could show that also they have the surface state in the metal, not as topological as a topological insulator, but even iridium oxide and ruthenium oxide are also having this nodal line. It's accidentally, it's maybe not accidentally, so but maybe this is a way to explain. Therefore, we thought if we look here for our chiral crystal, so maybe it's better than platinum, because we have those Y points at 2 different energy, and we have a very wide range of energy range where we see properly interesting properties. And we were able to do already electrochemistry, hydrogen evolution reactions. This everybody can do, I think. Okay, so we did hydrogen evolution reaction, and this material show quite good performance, even better than commercial platinum and so on. But it's still expensive in the sense it's maybe not what we want. So, but then we thought, okay, maybe we are doing more challenging thing. We go back to organic chemistry. We bought some dopamine, and we looked also electrochemistry here. We did L-dopa and D-dopa, and we reduced it by electrochemistry to a non-chiral system, and we used the 2 different crystals, and indeed in the 2 different crystals we saw an asymmetry. So there was always a higher reduction rate of one chirality on the corresponding chiral crystal than the other chirality. And we did also do this on thin films already, so because here it's even more clear on the thin films, because they are having only one surface, not many facets. And we compared it with platinum. In platinum, you don't see anything. In crystals, you see something. And the interesting thing is also, because we have this big magnet now for doing catalysis, we see also we can enhance the catalytic or the redox reaction in the magnetic field. Anyway, these are all unpublished data so far, or they were partially submitted for some patents, but anyway, this is, I think, interesting, and it's really going in the same direction like what another group at the EMPA does. They already looked with UHV methods on the asymmetry on the surface of palladium, gallium, and they see for this Hiskin circular addition, they see also strong high enantiomer specific reaction up to 5:1. So maybe this material is something where we could think about asymmetric heterogeneous catalysis. Okay, so with this I come to the future. So we also make a connection. This is for Ben, who knows also Ron Naman, eventually to the chiral induced spin polarization. And it's not totally crazy that maybe in electron, there are people in organic physicists who think if you have a chiral molecule and you measure a current, or if you have an excited state there, it's not in the ground state, that you have something like spin polarization there where spin and momentum is locked. And maybe there we could investigate more systems like our white semimetals, which are not chiral. Maybe they show also some chiral-induced spin selectivity. And then we would really make a bridge between our chiral electrons and the chiral molecules. So this is what we plan in the future. We started with Ben, and we do something with Ron. But it's also interesting that people saw in crystals a spin polarized current over micrometers. And I think Stuart will continue to talk about chirality. Maybe one can do something with superconductivity and with magnetism. So with this, I come to the end, and I thank my group and all my co-workers, including Stuart. He was on the other slide. And I thank you for your attention, and I hope I stayed in time.
Thank you very much. Claudia. That was pretty amazing. We're open for questions. I don't see any on the, I hope I'm on the right website. I don't see any on the website, so let's start with the audience. Sami, please, please use the microphone.
Okay.
Very interesting work. How much enhancements in the catalytic evolution for hydrogen evolution reaction, and how much magnetic field is needed, and is it a systematic enhancement by field strength?
So we didn't do the real full systematic because now we have the we started with a simple magnet, you know. So the last pictures then was the last measurement with the crystals were with a real big magnet. We have a 7 Tesla magnet now where we can tune the magnetic properties. Before we simply applied with a hard magnet. So the magnetic field we measured was 0.3 Tesla, and we saw an enhancement of the factor 2 in the white semimetal.
Factor of 2.
Yeah, but the white semimetal is even, okay, you have a change in the magnetoresistance effect, which means you have a change in the electron mobility, and it's still big at room temperature. So I think, is it surprising? So because the mobility plays a role if you do catalysis, so it's not so surprising, I would say. But it's interesting that you can make catalytic activity.
Are you aware of other reactions that there is enhancement with magnetic field?
No.
I'm not.
No, but therefore I simply think we are interested. Yeah. 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 And water splitting, they show that if you use chiral electrodes because of the spin selectivity, and they are also approaching now spin momentum locking, so they're approaching topology, so that you see if your electrodes are chiral, so because, and it's, for me, logic. So I think it's not magic, because especially if you have oxygen evolution reaction, you have a spin triplet if you make oxygen, okay? So that the spin in the intermediate state plays a role, and it makes a difference whether you have a paramagnetic or chiral material is not surprising also for me. So I believed this immediately. Okay, so this observation from Ron Naaman. But I think it's interesting to see more from the physical side on catalysis to maybe get new inspiration.
Thank you.
Other questions? No, nothing else? So let me ask a question. This PDGA, I assume it's the B20 structure.
Yeah.
So, and you also showed this sort of volcano plot, which you went by a little fast, that had the PDGA on it, right on the top. So, but we've also heard from others, like including this morning, that actually platinum intermetallics are on their own very active catalysts.
Yeah.
So how do we separate the role of a chiral structure from other effects in this particular case?
Yeah, here it's really like we have the palladium and the platinum, you are right. Yeah. So we really have to investigate more what is the origin, also for the chiral absorption, the preferred, whether it's the surface state. I went over my last slide maybe too fast. So we want to see, is this a surface state, is this the orbital angular momentum, which plays a role, or is it simply chiral structure? But in white semimetals, we don't have a chiral structure. So we could then finally go, but I want to go step by step because we really want to understand. But you're right, we are now looking for other systems, but therefore I went also very fast over the twisted graphene. But you know, if you take twisted graphene, it's chiral. And so in collaboration with Liang Fu, my former student Yan Zhang, we have even a calculation where we think we can be better than platinum if we twist niobium sulfide or selenide sulfide. So this might give us more possibilities even to so twisting the things, the 2D materials might give us, because I think graphene itself is difficult, it's not very reactive, but in the moment when you twist, you get this modulation of the, because we all chemists know that this is a very nice aromatic compound. Okay, so, but maybe for me, the twisted graphene is a little bit like anti-aromatic areas and aromatic areas, because you get the localized areas, and then you maybe have modulation of the charge carrier, and then you can achieve even without, because it shows the quantum anomaly Hall effect, then you maybe can achieve without heavy elements the effects, but I should not say too much. But this is maybe an interesting direction to go with twisted
A
graphene.
last question, but there's a microphone from Ben.
Fascinating. You know, we worked together with Ron Naaman on the spin transport and used our motors and switches to switch the direction of spin transport, you know, and it works. So we can tune it left or right. But what would you say, Luke, is your dream to make the effect larger? You mentioned aromatic compounds. We use aromatic compounds, of course, inherent chiral aromatic compounds. But what would be a key parameter to enhance the effect? Because the effects are still small, you know, when you look at the spin transport and so. What I try to get a feeling for that.
Yeah, but you know, Ron wants to have spin momentum locking and chirality induced spin polarization. So if it's true, so the results have to reproduce, because I think I would say that Andre would say, be careful if you measure a long mean free path of a chiral current in a non-local experiment, there might be contacts and so on, so you have to reproduce the things, but even having a long mean free path in a material with a chiral current is already giving you chiral electrons. But I still like also the twisted things, because you can modulate the electronic structure, and this might be, and then you even are chiral. You know, if you put it on boron nitride, you're chiral. I think there are a few people already recognizing that twisted graphene is chiral, but there are very few only. So we wrote a proposal now for the ERC, Pablo and me, maybe we get through. Anyway, to do this twisted graphene for catalysis and twisted 2D materials. So I think maybe this is a way, but also feed the things with chiral light, because we see in the photogalvanic effect that we can influence the Y points and the electrons and the chirality and the direction of the electrons so therefore we also have now an optical table for chiral light.
So you use these crystals. What about supramolecular assemblies?
Absolutely. So this is what my theoretician plan now. They are looking for organic materials and then go. I even think that we can even take, I go back to Roy Hoffman, who is my superhero, honestly. So he did surface science and inorganic science after he did organic chemistry. So if you think about the oxygen evolution reaction of Ron Naaman and the spin selectivity and the spin triplet, so if we look for a chemical reaction, we can apply the rules of topology. So a chemical reaction has also crossing points and so on, you know, and then you can play with light versus temperature and so on, and you might have a new viewpoint on the whole thing. It's nothing else, everything is there. Topology means simply we see suddenly things through different eyes.
So we should move on.
Thanks to graphene.
Thank you. We should move on, but there is a question that I want to ask, because it's coming through from the audience. This is from Weyl in Nankai. He says, "Dear Claudia, many thanks for your amazing talk. Can you give some comments about photocatalysis using circularly polarized light and chiral states?"
It should increase it.
It's a very interesting question.
Yeah, it's a very interesting question, and I think if you see already what Ron Naaman did, and then if you add even chiral light, you should enhance it. Okay, thank you very much.
Okay, so let's thank Claudia for an amazing talk.